So thank you very much, and we'll go to the next presentation. The next presentation will be led by Benoît Reitz, who is privacy engineer manager at Meta, so ex-Facebook, inside the Facebook Deletion Systems teams. So how are you, Benoît?
Hi, I'm doing all right. Yourself?
Great. So Benoît, you're going to speak about how you handle deletion at Meta. So I give you the mic. It's your turn.
Amazing. Thank you very much. So this is going to be a talk about deletion framework, which is how Facebook or Meta upholds its commitments towards user data deletion. Quick introduction, if this works. Yeah, quick introduction. My name is Benoît. I'm the engineering manager of the team called Deletion Systems, which is responsible for building the infrastructure required to run deletions. I've been working at Facebook for 7 years now, and most of my time spent in deletion and privacy. Deletion framework is the framework responsible for graph deletions. So imagine you want to delete your Facebook account. We need to identify what's the logical subgraph that represents your data. And then this is going to be spread across many machines and many data stores. And we need to ensure that there is no trace of you after a given amount of time. In terms of scale, deletion framework handles 500 billion new graph deletions per day, which accounts for approximately 1 trillion individual objects that we delete per day again. And we handle a dozen of interconnected data stores, which hold the entirety of the Facebook graph. Finally, this talk is going to be a bird's eye view of many systems rather than a deep dive. So without further ado, let's get started with the design overview of deletion framework. First of all, I'd like to talk about how we rely on a data definition language. And this was a very early learning in the lifetime of this team, which was we cannot require developers to care about privacy or care about deletion. And at first, when we started doing this, we asked developers to write their own deletion logic. And with this, there was many issues. One of which was people write bug in the deletion logic, which is really, really bad because you want the deletion logic to be very reliable so that they run without any issue. But also the deletion logic and the data definition would just drift apart. Like product teams would update their products and the data that they collect and hold, but they wouldn't go and update the deletion logic. So what we transitioned to is code generation. So there is a data definition language at Facebook that we basically piggybacked on and added deletion annotations. So the annotations we use is the storage configurations, which basically tells us where is the data stored, which already existed before us. But then we added the deletion edge annotations, which tell us given edges in the graph, how to traverse them, and then deletion constraints, which is a way for developers to protect their data. If we look at an example here, 3 schema, user, post, and comments, we can see that they have edges between them. So like the from user to post edge is going to be what we call a deep edge, which means that once we see this edge, we want to traverse it and recursively delete whatever is on the other side of that edge. Conversely, we have the from post to user soak, so like the inverse of this one, which is a shallow soak, because when we delete a post, we actually don't want to delete the author. And those edge annotations is what tells us how to iterate over the entire graph. We can see the other annotations on those schemas. There is the storage, which in this case is Tao, our biggest graph database at Facebook, and then the constraints. So if we take an example where here the user constraint is never deep deleted, what this basically means is never will a user be deleted as part of another object's deletion. So users will always be the top level object. So you never want to delete a user when you delete a post, right? And this basically safeguards against misconfiguration, right? We can see on the post, for instance, we have deep deleted by any other entity. This basically means that the post schema accepts deep edges from anyone, but they require at least one. And then comments is another type of constraint, which is deep deleted by post, which basically means that developers are able to safeguard what are the object types that can delete their data. And then we use all of those annotations to generate code. And there is the user deleter and the post deleter in those examples, which are completely generated. And what those deleters do is they mostly delegate work to other parts of the infrastructure. And in this case, they would end up delegating the work to what we call primitive deleters. Primitive deleters are interaction points between deletion framework and the different storages that we integrate with. And those primitive deleters are written by the deletion framework team in their effort to expand the coverage of the deletion framework. And those are the actual deleters that do work. So basically, generated deleters iterate over the graph, and once we reach a leaf, we execute a primitive deleter that issues the delete to the data store. Let's now look at how we actually walk over the graph. And we use a DFS because it is a simple algorithm to implement, and it's quite cheap to run in comparison to, for instance, a BFS. We need to be reentrant because we delete very large graphs, which we are not going to be able to delete in a single run. And we need at least one semantic. So every object needs to be deleted at least once. And if we take this example graph here, where we have a deletion request on a post, what's going to happen is, first, the framework is going to read the data of what we're trying to delete. So in this case, the post. We're again going to do a checkpoint on a persistent stack. So this stack here is basically the stack you would see in a DFS. The only difference is that it's in a blob storage somewhere. And this is what allows us to be reentrant. So let's assume that the job gets killed halfway through for any reason. We can restart the deletion and read the stack and know exactly where in the graph we were. And there is the data that we need to iterate over the graph that's also preserved in this persistent stack. Then we log restoration logs before actually doing any deletes. Those restoration logs, as we're going to see later, allow us to basically restore data. And then we do the self-deletion. After the self-deletion, the graph deletion is what happens. And for the graph deletion, we basically read the schema definition and list all of the soak types we need to fetch. So here, there's the soak with the author, and this is a shallow soak, so we're just going to delete the soak. So first log restoration log, then delete the soak, move on to the other soak type, in this case, the soak to comment. Those are deep soaks. So we first traverse them, read what's on the other side, put it on the persistent stack, log the restoration logs, delete the object, and do the graph deletions recursively from there. In this case, there is just an soak to the author, which we delete as it's a shallow soak. Once the deleter is done, we basically pop it from the stack, and then we go back up, log the restoration logs for the soak that led us to this, and then we can delete the path that led us to delete those objects. After that, we basically continue iterating, and it's basically the same. So we go down, delete objects on the way down, persist everything on the stack, and then on the way up, pop the soaks, pop the objects from the stack. And finally, once the top level deleter is popped from the stack, this is a sign that the deletion is actually over and that we deleted everything that we needed. That's basically how it works. As you've seen, there's like a lot of round trips that happen in this, which is why we introduced the concept of batching. And the way it works is all of those actions, read, checkpoint, log restoration logs, and do the deletes that are going to be done in order like this. So first, the framework is going to read a lot of data, and it's going to stop until either we aggregated enough data that we reached a payload size that makes sense, or until we reach a deleter who cares about the ordering of the deletes. Not all of the deleters do that. Like a vast majority of the deleters don't care about ordering, but some do. And for those, we need to stop the batching to basically maintain the ordering. Then we checkpoint everything on the stack. You might see here that the order of the nodes of the stack doesn't respect the DFS anymore, which again is fine because we know that those deleters don't care about ordering. This allows us to retry the deletion if any of the deletes fail. After that, we log the restoration logs in one much bigger record, delete everything at once. Some things might fail, in which case the deletion bails and then restarts, and then pop everything and then keep on going. And that's basically how we can go much, much faster than we would otherwise. Now let's quickly take a look into how we schedule deletions in the future. And scheduling deletions in the future is essential to enable ephemerality at Facebook. And think Instagram stories or the account deletion grace period, right? So like when you try to delete your account, you have 30 days to re-log in to cancel deletion. We support scheduling years in the future, which is very useful for financial data, for instance. We also support custom TTM logic, which allows product team to do very powerful stuff like delete this post 9 days after the last comment on the post, for instance, which basically requires us to continuously check. And in terms of scale, we process 160 billion events per day, and this has been growing much, much faster than the rest of Deletion. This is a quick overview of the infrastructure. It's really a tremendously big data pipeline. But to recap, there is the aggregation pipeline that gather all of the creations. The status pipeline is what looks at everything that's in flight and look at things that were scheduled, things that failed, things that need to be scheduled. The retry and just-in-time pipeline are the pipelines that are responsible for taking things from the status pipelines and basically schedules them to be executed later. That's pretty much it for the design overview. Again, those were like a few pieces of the framework. There are many other moving pieces, but those are like the most important. And now we're going to see the different guarantees that we provide and how we monitor them. And the first one I want to talk about is the scheduling. So the deletions run in two phases. There is the sync part, which runs in the web request. And then there's the async part, which iterates over the graph. Why do we have this? We have this because it's not possible for us to execute all of the graph during the web request, right? We want to return as fast as possible. And in most cases, the sync part is just going to be responsible for deleting the top level object. And to do this, you just need to write the metadata, log the deletion request, delete the top level object, and then schedule the async job to delete the rest later. And that's how we guarantee that we can accept the deletion request and spend as little time so that it's not interrupting users. And the sync part is responsible for hiding the subgraph. So whenever we delete the post, we want all of the comments and replies to be hidden. Even if you have like a direct link to the content, we want to have something that prevents people from reading that content. And the way we achieve this is using privacy policies. So privacy policies is a feature that belongs to the privacy layer of Facebook, which is offered by the data definition language. And that privacy layer is what enables Facebook to say, photos are hidden if you're not friends with that person. This is the layer that executes all of those privacy checks that defines if things are visible or not. And this is what we use to do real-time validation on that content while it waits to be deleted. There's one issue, which is that the privacy layer is distinct from the deletion graph. We have efforts to try to merge them together so that given the definition of the deep edges and their presence or not, we can define whether or not that should be visible on the platform. But this is a very complicated problem, and this is not mature enough yet. So what we do basically is whenever we run deletion, we do sampled checks on the data. So try to load the data using the viewer context of the person who scheduled the deletion. And if we can load any of that data, this basically means that the privacy policies aren't correct for this, because we shouldn't be able to load a subgraph that is about to be deleted. And so we basically escalate this for people in the company to resolve this. And that's how we guarantee that the data is hidden properly. Now I want to talk about eventual completion. And this is a big one, because deletions might run into many issues. And infrastructure in our world, right, has some reliability guarantees, which counts a number of nines, right? But users, when we delete their data, they don't want 4 nines of reliability, right? And we shouldn't give them 4 nines of reliability. We should give them 100% if we can. And to do this, we need to build safety nets to basically go around all of the issues that we have. So infrastructure issues, or like bug in the deletion code, or like deletions that get dropped by dependencies, or like that fail halfway through the scheduling and are left in a weird, inconsistent state. Every deletion started must eventually complete. And the way to do this is we log every event from the lifecycle of deletion into a huge table that we call deletion history. And then we have a pipeline that computes a daily status for every deletion that is in flight. And we extract 2 data sets from there. The first one is the idle deletion, which is the deletions that haven't been executed in some amount of time, right? And what we do with those is we reschedule them. That's the first layer of defense, right? Which is try to mitigate the issue automatically. But we also have some monitoring there that tells us what is the deletion that has not been running for the longest in the entire framework. And we have like some alerting on this, because even when you have safety nets, those safety nets might fail, or the remediation that you have might fail. And this is a key learning that we had. The second set is stack deletions, which is basically aggregating all of the deletions that run into persistent infrastructure issue, tries to aggregate them into units of work, predict who in the company would be the best person to tackle this problem, assign a task to them with the debugging tool and information they need to be able to debug that deletion. And then we have a whole program on top of this with SLAs so that we can make sure that product like infrastructure issues preventing deletions from going forward are resolved within an SLA, which in turn allow us to provide some SLA around the completion time of deletions. Let's look at eventual completeness now, which is the second part of eventual completion. Eventual completion looks at making sure that jobs finish. Eventual completeness makes sure that we delete all of the data, regardless of whether the job has finished already or not. And there's many issues that can lead to orphan data, right? So bugs in the deletion logic, race conditions between different systems, right? So we could be trying to delete a subgraph, but then some other system somewhere like writes data that points to that subgraph, or deletion settings misconfiguration. And you can try to prevent all of those, right? But you are going to end up with some orphan data in data systems that you hold. And we need to clean that up retroactively. And the solution we have is object redeletion. So we know of every object we deleted since the beginning of time because we have an auto increment column, which is the identifier of the objects. And then from all of those objects, we try to fetch associations that are pointing to or from those objects. And then we basically reapply the deletion logic. So if the association is deep, we're going to basically walk the graph and redelete everything that's on the other side of that soak. If the deletion is shallow, we're just going to redelete the shallow soak. They run on every object type that Facebook holds. They start every other week, and they iterate over all of the data that we hold to try to proactively mitigate orphan data like this. This is really a massive, massive endeavor that does clean up much more than we would expect given the systems that we have. But this is just an artifact of having so many different systems that interoperate and that are hard to synchronize. And then I want to talk about restorations quickly. If you operate systems that's deletion at a large scale, you are going to have data losses. They are inevitable to some extent, right? You might have a product bug, for instance, where there's a UI element that accidentally schedules deletion when it shouldn't, or you might have engineers that misconfigure their deletion configurations, right? And to do this, we log restoration logs before every delete that we issue, as we've seen. And those are a bit different from your usual data store backup because they are graph indexed. So a graph in those logs are one entity that you can restore. And they do also spawn multiple data stores. So you can restore a graph that has been deleted from like 4, 5, 6 different data stores at the same time. The way it works is we basically have a write-ahead log from our deletion execution flow that aggregates smaller payloads and a tailor that is responsible for aggregating them into bigger payloads so that it makes sense economically to write them to a data store because we just cannot write them directly because they're way too small. And one of the interesting issues we ran into is we hold backups of deleted data, right? But we want to have a very, very strict upper bound on how long do we retain user data. If we hold backups in a data store, that data store might have backups, and then you have a weird lineage problem that you need to try to solve. The way we solve this is we use an encryption service that provides us with a daily rotating encryption key, which we are the only person to have access to. We encrypt all of our data like this using the key of the day. And that key has a TTL so that once the key expires, we have deletion by encryption that basically happens. And whoever might have copied our logs somewhere in a backup table or somewhere else, right, would not be able to get data. And that's how we enforce that user data is deleted after some amount of time. We have some ways of preventing data loss. None of them is foolproof. So we static analysis on the deletion graph. We do dynamic checks at runtime. And we also look at the way the graph is to run predictions on the edges deletion behaviors to try to find misconfigurations that might have been otherwise unnoticed. Monitoring guarantees, that's a very important part of our work, right? We need to be able to prove to our users and to assessors that we are actually meeting the bar for our users, right? Those are like all of the metrics we monitor. I mean, some of them, I don't want to get into those, but the point I want you to take away is we have a happy path right? And we need to measure its reliability, but the happy path is not going to be enough. And we need to measure how much falls through the gaps. And then we need to have safety nets that automatically remediate that. But we also need to measure that safety net's reliability. And if possible, have more safety nets behind. And bonus points if your way to measure success is completely orthogonal from your system, right? Like if you have a source of truth which doesn't rely on your system, that's much, much stronger. And having multiple layers of safety nets is also a very important point. In conclusion, deletion is really a hard problem. The happy path is not enough, and we need to make it easier for developers to do the right thing than do wrong things. And that's a learning that also exists in security, right? You can train your engineers as much as you want to not ship security flaws, but this is going to happen, right? And you need to embed privacy at the infrastructure layer the same way we embed security at the infrastructure layer, so that when engineers use those infrastructure, they have by default products that are privacy aware or security aware. I'd like to thank everybody who contributed to the Deletion framework over the years. We've really made a tremendous amount of progress, and I'm really proud to have been working on this project for so long. This is my email address. If you have any follow-up questions, feel free to send them there.
Thank you very much, Benoît. It was very, very interesting, and we learned lots of things. We have 3 minutes left for a Q&A, and one of the first question was asking for precision. So here, are we talking about hard deletions, or are we talking about deletion for from a production system? Yeah, so is it hard deletion or kind of soft delete or something else?
No, this is hard deletion, and this is hard deletion both coming from user-generated traffic, so people pressing deletes on platform, but also other production systems that might want to deprecate entire data types and the graph associated to them.
Okay, and another question was about how Facebook, what is the granularity you have on deletion? I mean, like some countries, some regulations oblige companies to keep some of the data. So when a user asks you to delete some data, you have to delete some, but you have also to keep some depending on the country the user is. So how do you handle the differences between all these country and local regulations?
Yeah, that's a very good question. And the answer to this is we have something that's called an internal policy, which is a document that's written by policy, lawyers, and engineering that defines what is the standard that the company is going to meet. And lawyers are responsible to make sure that that standard fits every regulation. And that way, engineers don't need to understand regulations. They need to just meet one standard. And that's how the company works. And this is really a game changer. You don't want engineers to have to understand GDPR or CCPA at the same time and understand the intricacies of it.
Okay. So yes, so engineer doesn't. That's not that they doesn't care, but they don't put their hands in the complicated
They're
regulation.
abstracted away from engineering.
Okay, so thank you very much. It's just time. So thank you very much. I saw one or two more questions in the chat. So if you have just 5 minutes before leaving to answer them in the chat, it would be really great for the community. So thank you very much again, and I wish you a very pleasant day.